There is a connection written into the very fabric of our universe. It is a link so profound, so immediate, and so utterly strange that it seems to violate the fundamental laws of reality itself. This is not a bond of gravity holding planets in their silent waltz, nor is it the flickering exchange of light across the cosmic dark. It is something else entirely. An unseen tether, a ghostly whisper that travels across any distance, no matter how vast, in no time at all. Imagine, if you will, two particles of light, two photons born from a single event, a single flash of atomic violence. They are twins forged in the same quantum furnace, sharing a single unified existence. Now, let them fly apart. One travels towards the heart of our own Milky Way, the other hurtles in the opposite direction toward the infinite void. They journey for 1,000 years, 1,000,000, 1,000,000,000, crossing the chasm between galaxies, through stellar nurseries and cosmic graveyards, until they are separated by distances we can barely comprehend. They share no physical medium, no string, no energy beam connecting them. According to everything we know, they are now two separate, independent entities, lonely travelers in the immense silence of space. But they are not. They are still one. If you were to reach out and intercept one of these photons here near Earth and measure a specific property like its polarization, its orientation in space, you would find its state is completely random. It could be vertical, horizontal, or anything in between a roll of the cosmic dice. Yet, in the very same instant, the exact same nanosecond that your measurement is made, its twin, now separated by unimaginable emptiness, billions of light years away, instantly assumes a correlated state. If you measured yours to be vertical, its counterpart across the universe would immediately become horizontal. Instantly, not at the speed of light, faster, so much faster that the very concept of speed becomes meaningless. The information, the knowledge of what you did here, seems to have been communicated across the cosmos in zero time. It is a perfect, instantaneous cosmic mirror. This unsettling phenomenon, this impossible dialogue between distant particles, is known as quantum entanglement. It is not a theory, not a speculation, but a proven, observable fact of our world, demonstrated time and again in laboratories around the globe. And yet, it drove the greatest scientific mind of the 20th century to distraction. It haunted the man who redefined space-time and gravity. Albert Einstein, the architect of relativity, the titan who taught us that nothing, absolutely nothing, can travel faster than the speed of light, found this idea utterly repugnant. He saw it as a phantom limb of physics, a flaw in the otherwise elegant mathematics that described the subatomic world. To him, the universe was supposed to be a reasonable place. It was vast, yes, and filled with wonders beyond imagination, but at its core it was governed by cause and effect, by laws that were local and logical. An event happening here could only affect its immediate surroundings. For a ripple to travel across the pond of space-time, it needed time to travel. This was the bedrock of his revolutionary theories, the principle of locality, a constraint so fundamental it felt like common sense. The speed of light wasn't just a cosmic speed limit. It was the very scaffolding of causality, the law that prevents the future from influencing the past, the rule that keeps the universe's story coherent. And entanglement seemed to shatter that scaffolding with casual disdain. It suggested a universe where a flick of a wrist here could have an immediate consequence on the other side of existence. It was a universe that to Einstein seemed to play with loaded dice. In a now famous letter to his colleague Max Born, Einstein gave this quantum absurdity a name that would echo through the ages. He called it spukhafte Fernwirkung, spooky action at a distance. The phrase was not a compliment. It was a declaration of disbelief, a challenge hurled at the new priests of quantum theory. It was the cry of a man who looked into the heart of this new physics and saw not a deeper truth, but a ghost in the machine, a breakdown of the very logic that had guided him to unlock the secrets of the cosmos. He was convinced there had to be a simpler, more sensible explanation. He believed the universe wasn't being spooky. The theory was simply incomplete. His intuition, the same intuition that had overthrown Newton and envisioned gravity as the curvature of space-time, was now screaming that something was profoundly wrong. To understand Einstein's profound discomfort, let's consider a more familiar scenario. Imagine we have a pair of gloves, one right-handed, one left-handed. We place each one into a separate, identical box without looking. We then shuffle the boxes and send one to you and the other to the far side of the moon. You journey to your lunar outpost, and I remain here on Earth. At a prearranged time, you open your box and find a left-handed glove. In that exact instant, you know with absolute certainty that my box contains the right-handed glove. There is no mystery here, no spooky action. The information didn't travel from your box to mine instantaneously. The outcome was predetermined from the very beginning, from the moment the gloves were placed in the boxes. The information about which glove was in which box was always there, hidden from us until we chose to look. This is what Einstein believed was happening with entangled particles. He proposed that they were like these gloves, that they carried some hidden variables, some secret instructions from the moment of their creation. Their properties, he argued, were not random at all. They were fixed, determined, but unknown to us, the observers. The apparent randomness was just a veil concealing a deeper classical order. The universe, in his view, was not gambling. We were simply ignorant of its hidden cards. It was a brilliant, intuitive, and deeply comforting idea. It preserved locality. It upheld causality. It saved the universe from the madness of instantaneous connection. There was just one problem. The universe does not care about our comfort. And as we will discover, Einstein, for once in his monumental career, was wrong. The quantum world is not like a pair of gloves in a box. The terrifying, exhilarating truth is far stranger. An entangled particle does not have a definite state, like a left or right glove before it is measured. It exists in a ghostly haze of all possible states at once, a shimmering cloud of probability. The property we measure, its spin, its polarization, is not a pre-existing reality we unveil. It is a reality we help create in the very act of observation. The particle does not decide to be vertical or horizontal until the moment it is forced to. And in that moment of becoming that instant of decision, its distant twin light years away is somehow notified and makes its own correlated choice from its own cloud of possibilities. This is the heart of the spookiness. It's not that the information was hidden. It's that the information didn't exist anywhere in the universe until the instant we asked the question. And when it sprang into existence here, it also sprang into existence over there. This truth shatters our classical intuition like glass. It forces us to confront a reality that feels more like magic than mechanics. What does separation even mean in a universe bound by these invisible threads? If two particles separated by the breadth of a galaxy can still behave as a single entity, are they truly separate at all? Or is the space between them an illusion? A convenient fiction our minds have constructed to make. A sense of a world that is at its deepest level, profoundly whole and interconnected. This isn't just a philosophical question. It is a direct challenge to our most fundamental concepts of space, time, and identity. It suggests that on some deeper, hidden level of reality, a level we are only now beginning to probe, the universe might not be a collection of separate things, but a single, sprawling, entangled quantum object. What happens in one corner of the cosmos might not be an isolated event, but a note played in a symphony, whose score is written across the whole of space-time. The implications of this cosmic link are staggering, stretching far beyond the esoteric debates of theoretical physics. This spooky action is no longer a mere curiosity. It is being harnessed, engineered, and transformed into the foundation for a new generation of technologies that will redefine our future. The principles of entanglement are the beating heart of quantum computers' machines that promise to solve problems so complex they would take a classical computer longer than the age of the universe to crack. It is the key to creating unhackable communication networks, where the very act of eavesdropping would instantly break the delicate, entangled link revealing the intruder. It even breathes a whisper of possibility into ideas once relegated to science fiction like quantum teleportation, the disembodied transport of information from one point to another. The ghost that haunted Einstein has become the engine of the 21st century. So how can this be? How does the universe pull off this impossible trick? Is there some hidden communication channel, some secret network that operates outside the known laws of physics, a cosmic subterfuge that fooled even Einstein? Or is the answer even more radical? Could it be that our very notion of Space as a vast empty stage is wrong. Perhaps space is not the fundamental reality we perceive it to be, but an emergent property, a grand illusion painted on a deeper canvas where everything is and always has been touching everything else. Perhaps here and there are not absolute truths, but simply perspectives within a unified, entangled whole. This is the mystery that lies before us. It is a journey that will take us from the mind of a genius wrestling with a paradox through decades of brilliant experiments designed to put this spookiness to the ultimate test, and finally to the frontiers of modern physics, where we stand on the precipice of understanding a new and shocking reality. We must let go of the solid, predictable world we think we know. We must be willing to embrace the absurd, the counterintuitive, the utterly bizarre. For in the heart of this quantum weirdness, we may find the most profound truth of all, that the universe is not a lonely collection of isolated islands in a dark sea, but an intricate, interconnected web, a single magnificent tapestry. The journey to unravel that tapestry begins now. We will follow the clues, peel back the layers of the mystery, and confront the spooky action at a distance head-on. The story of how we proved Einstein wrong, and in doing so stumbled upon a deeper, more magical reality than he ever dared to imagine, is the story of science at its most daring and its most humbling. It is a quest to understand not just the particles that make up our world, but the very nature of connection itself. What if reality itself has a secret, hidden layer of connection that defies our most fundamental intuitions about space and time, a ghost in the machinery of the cosmos? In the early 20th century, a revolution was underway, not one of fife and drum, but of chalk and blackboard. A new science, quantum mechanics, was being born, and its revelations were tearing down the marble pillars of classical thought that had stood for centuries. This was a world of probabilities, not certainties, of things existing in a haze of potential until the moment they were observed. It was a chaotic, dizzying, and exhilarating time, a period of intellectual ferment led by a new generation of scientific rebels. Niels Bohr, with his model of the atom, became the movement's philosophical patriarch in Copenhagen. Erwin Schrödinger in Vienna penned the equation that would govern this new ghostly realm, even as he famously expressed its absurdity with a cat that was both alive and dead. Werner Heisenberg gave us the uncertainty principle, a formal declaration that at the smallest scales, nature refuses to be pinned down forever, withholding some of its secrets from our simultaneous gaze. They were building a new cathedral of knowledge, one whose architecture was made of probability waves and quantum leaps, and it was a structure that one man, arguably the greatest scientific mind since Newton, could not bring himself to enter. That man was Albert Einstein. He was the iconoclast who had shattered the old universe, the visionary who had warped space and time with his theories of relativity. He, more than anyone, had earned the right to redefine reality, yet this new quantum world, a world he had helped to midwife with his early work on the photoelectric effect, now seemed to him a monstrous and incomplete child. He saw not a deeper truth, but a surrender to chaos, a retreat from the grand, intelligible design he so profoundly believed the universe must possess. For Einstein, the cosmos was a sublime and intricate clockwork, governed by immutable laws. The idea that its fundamental gears operated on chance, that reality was a cosmic lottery, was anathema to him. It was a philosophical insult. His famous declaration, "God does not play dice," was not a casual remark. It was a cri de coeur, a defiant statement of faith in a rational, predictable, and comprehensible universe. He saw the architects of quantum theory as brilliant but tragically misguided. He believed they had become so entranced by their powerful new mathematical tools that they had mistaken a temporary description for the final word. They were, in his view, like explorers who had found a new continent and, marveling at its strange flora and fauna, declared the rest of the globe non-existent. Einstein was convinced there was more, something deeper, something hidden, and in 1935, from the quiet halls of the Institute for Advanced Study in Princeton, he decided to launch his most powerful intellectual assault on the new physics. He would not do it alone. He joined forces with two younger colleagues, the brilliant but troubled physicist Boris Podolsky and the quiet, methodical Nathan Rosen. Together, they would draft a paper, a thought experiment so elegant and so devastatingly clever, it would send shockwaves through the world of physics that are still felt today. It was published in the Physical Review under the title, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It would become known to history simply as the EPR paradox. It was not an attack on the mathematics of quantum theory. The paper conceded that the equations worked. They gave stunningly accurate predictions. Instead, it was a profound philosophical challenge, an arrow aimed directly at the theory's heart. Einstein, Podolsky, and Rosen designed their thought experiment to expose what they saw as a fundamental absurdity, a logical contradiction so glaring that it must prove the theory was merely a stepping stone to a more profound truth. They decided to use one of the strangest predictions of the new quantum theory against itself. A bizarre, almost telepathic connection that the equations allowed between two particles, a property we now call entanglement. At the time, it was a theoretical curiosity, a piece of mathematical weirdness that had not yet been given a name. But for Einstein, it was the perfect weapon. He saw in it the seeds of quantum mechanics' own undoing. He and his colleagues argued that if you took quantum mechanics at its word, you were forced to accept consequences that violated the very foundations of reality as we know it. They asked you to imagine a scenario, not a real experiment with lab equipment, but a pure exercise in logic. Imagine you have a process that creates two quantum particles, let's call them particle A and particle B, that are intrinsically linked. They are born from the same event, and their properties are perfectly correlated. For example, imagine they have a quantum property called spin, which when measured can be found to be either up or down. If the system is prepared in a certain way, quantum mechanics dictates that if you measure particle A and find its spin is up, you will know with absolute certainty that particle B's spin is down. And if A is down, B must be up. They are a matched pair, their fates forever intertwined. They exist in a single shared state described by one mathematical equation, one wave function. Until they are measured, neither particle has a definite spin. They are, in a superposition, a ghostly blend of both up and down simultaneously. It is the very act of measurement on one particle that seemingly forces both of them in that instant to snap out of this haze of potential and into a definite state. This is the orthodox Copenhagen interpretation championed by Niels Bohr, and this is precisely what Einstein found so unacceptable. Here is where the EPR argument becomes a masterpiece of intellectual demolition. They say, let us take these two entangled particles, our perfectly correlated pair, and separate them. Let's not just move them to opposite ends of a laboratory bench. Let's send them hurtling in opposite directions at nearly the speed of light. We send particle A to a laboratory on Earth, and particle B to a research station on Alpha Centauri, over 4 light-years away. For years they travel, each existing in that undefined quantum fog. Neither has a definite spin. They are pure potential, their shared story not yet written. Now an experimenter on Earth decides to measure the spin of particle A. The moment her detector interacts with the particle, its wave function collapses. The dice are cast, and the particle is forced to choose. Let's say the result is up. According to the rules of quantum mechanics, in that exact same instant, particle B, 4 light-years away, must immediately assume a spin of down. The outcome of the measurement on Alpha Centauri is now a foregone conclusion. The physicist there has not done anything yet, but the fate of their particle has been sealed by an action that took place trillions of miles away. This is the spooky action at a distance that so haunted Einstein. This instantaneous connection, this faster-than-light communication of information, seemed to violate the most sacred law of his own theory of relativity. Nothing, absolutely nothing, can travel faster than the speed of light. The cosmic speed limit was for Einstein non-negotiable. To suggest that the measurement of a particle on Earth could instantaneously influence its partner across a vast gulf of interstellar space was to him a regression to magical thinking. It was a phantom, a ghost in the equations that could not possibly represent the real world. So Einstein, Podolsky, and Rosen presented a stark choice. Either you accept that the universe engages in this spooky action, this instantaneous non-local influence that breaks the light-speed barrier which they considered absurd, Or there is another far more sensible explanation. The choice quantum mechanics forces upon us, they argued, reveals its own incompleteness. Their alternative was rooted in two bedrock principles that they believed any sensible theory of reality must obey locality and realism. The principle of locality states that an object can only be directly influenced by its immediate surroundings. For an event here to affect an event over there, something, a particle, a wave, a force, must travel through the intervening space to carry that influence, and that travel cannot happen faster than light. Your reading of this script cannot instantaneously cause a bell to ring on Mars. An influence must propagate. The principle of realism, sometimes called objective reality, is even more fundamental to our intuition. It asserts that objects have definite properties that exist independently of our observation. The moon has a definite position and momentum even when no one is looking at it. A tree falling in the forest does make a sound, whether or not an ear is there to hear it. Reality is not a performance staged for our benefit. It exists solid and unambiguous on its own terms. The EPR paradox was engineered to show that quantum mechanics forces you to abandon at least one of these cherished principles. The orthodox quantum view championed by Bohr was to abandon them both. Bohr would argue that it is meaningless to speak of the spin of the particle on Alpha Centauri times before times it is measured. Its properties are not real until they are observed. And the two particles are not truly separate entities, no matter how far apart they are. They remain a single quantum system, so influencing one part of the system is not a local action in the classical sense. There is no signal that needs to travel between them, because in a quantum sense there is no between. This was precisely the kind of philosophical fog that Einstein refused to accept. He, Podolsky and Rosen offered their alternative, a solution that preserved both locality and realism. Their conclusion was inescapable. The particles must have had their properties all along. The seemingly spooky connection, they argued, is not a connection at all. It is an illusion born of our incomplete knowledge. The outcome of the experiment was predetermined from the very beginning. When the two particles were created, they were created with a definite set of instructions. Think of it like this. Imagine we have a pair of gloves, one right-handed and one left-handed. We place them into two identical sealed boxes, shuffle them and send one box to Earth and the other to Alpha Centauri. You have no idea which box contains which glove. When the scientist on Earth opens their box and finds a left-handed glove, they know instantly that the box on Alpha Centauri must contain the right-handed glove. Does this instantaneous knowledge mean a spooky signal traveled between the boxes? Of course not. The information was always there. The property of right-handedness was a real pre-existing element of reality contained within that distant box long before it was opened. The mystery was simply in our lack of knowledge. This, Einstein argued, is what must be happening with entangled particles. There must be hidden variables, local elements of reality that quantum mechanics was failing to account for. These hidden variables are the secret instructions, the genetic code of the particles, telling them exactly how to behave when a measurement is made. The spin of particle A was always up, and the spin of particle B was always down. They carried these properties with them from their moment of creation. The correlation we observe is not spooky. It's simply the revelation of a pre-existing, classically sensible state of affairs. Therefore, quantum mechanics, by failing to describe these hidden variables, is an incomplete theory. It's a powerful statistical approximation of a deeper, deterministic, local and real universe. It gives us the odds, but it doesn't tell us the whole story because it is blind to the underlying machinery. The EPR paper was a declaration of war on the foundations of the Copenhagen interpretation. It was Einstein's elegant, logical, and powerful attempt to restore common sense to the universe. He was not trying to disprove quantum mechanics. He was trying to save it from its own apparent absurdities to complete it. He was offering a way out of the spooky, non-local fog and back into the clear light of a reality that behaved the way we intuitively feel it should. The paper dropped like a bomb into the world of physics. It divided the community. Many physicists, uncomfortable with the bizarre implications of entanglement, were swayed by the sheer force of Einstein's logic. It seemed so reasonable, so obvious. How could reality be otherwise? Niels Bohr, however, was reportedly stunned by the attack. He abandoned all other work and with his colleagues painstakingly crafted a response published under the exact same title as the EPR paper. Bohr's rebuttal was dense, subtle, and steeped in a new kind of physical philosophy. He argued that Einstein's very criteria for what constitutes reality were flawed when applied to the quantum realm. You cannot, Bohr insisted, separate the particle from the measurement apparatus used to observe it. They form an indivisible whole. To ask what the spin of a particle was times before times you measured it is a meaningless question like asking the marital status of a bachelor. The debate raged, but it remained a debate in the realm of philosophy. Einstein's hidden variables were by their very nature hidden. How could you ever design an experiment to test for something you couldn't see? The EPR paradox was a perfect self-contained thought experiment. It presented a clear philosophical choice, but it offered no physical path forward. Einstein had drawn a line in the sand, separating two entirely different conceptions of the universe. On one side was his universe, local, real, deterministic, and ultimately knowable. A place where things have properties, where causes precede effects in an orderly chain, and where the moon is most definitely there when we are not looking. On the other side was Bohr's universe, a strange, holistic, and irreducibly probabilistic world where particles exist in a ghostly limbo until they are measured, where distant objects can be intimately connected, and where our very notion of an independent reality is a classical illusion. For decades, this schism remained. It was a matter of taste, of philosophical inclination. You could choose your universe. Einstein went to his grave in 1955, convinced that quantum mechanics was just a temporary phase, and that a deeper, more complete theory would one day be found vindicating his classical intuition. His argument was so powerful, his logic so compelling, that for many it seemed the final word. But the universe is under no obligation to conform to our common sense. The thought experiment had been set. The challenge had been issued. What no one could have predicted was that decades later, a brilliant physicist from Northern Ireland would find a way to drag this ethereal philosophical debate out of the realm of thought and into the stark, unforgiving reality of the reffing laboratory. He would devise a test, a way to actually ask the universe itself which side it was on. A way to finally force nature to show its hand and reveal whether Einstein's beautiful, sensible reality or Bohr's spooky, entangled cosmos was the one we truly inhabit. And so for decades the paradox lingered, a ghost in the machine of quantum mechanics. Einstein's challenge, his spooky action at a distance, was not refuted so much as it was sidelined. The majority of physicists, swept up in the incredible predictive power of the new quantum theory, adopted a pragmatic, almost dismissive stance. The equations worked. They predicted the outcomes of experiments with flawless precision. Why waste time on what some considered mere philosophical navel-gazing? The deep, unsettling questions about the nature of reality posed by the EPR paradox were filed away, relegated to the closing chapters of textbooks, a curious historical footnote. The quantum world was strange, they conceded, but it was a strangeness we had to accept, not necessarily understand. A generation of scientists learned to stop asking why and simply shut up and calculate. The profound schism at the heart of physics lay dormant, a cold war of ideas fought not in laboratories but in the hushed corridors of academia. Reality, it seemed, could wait. But it could not wait for a quiet, fiercely intelligent physicist from Northern Ireland named John Stuart Bell. Working by day amidst the colossal energies of the CERN particle accelerator in Geneva, designing the magnets that would steer protons at nearly the speed of light, Bell spent his nights haunted by a deeper mystery. He was an engineer of the quantum world, a master of its practical application, yet he could not shake the feeling that his colleagues had surrendered too easily. He felt the full, unnerving weight of Einstein's objection, not as a philosophical preference, but as a deep wound in our understanding of the universe. To Bell, declaring the debate over without a definitive proof was an abdication of scientific duty. It was an intellectual armistice, not a victory. He saw that the core of the disagreement wasn't just about interpretation, it was about the very fabric of existence. Was the universe a cosmic game of chance, where properties spring into being only when we look as Bohr and the Copenhagen school contended? Or was there a deeper, more orderly reality hidden from our view, a set of instructions that particles carry with them, as Einstein fervently believed. This latter idea, Einstein's vision, is what physicists came to call the theory of local hidden variables. The concept is deceptively simple, an appeal to our most fundamental intuition. Imagine you have a pair of gloves, one right and one left. Without looking, you seal them in two identical boxes and mail them to opposite ends of the earth. When your friend in Tokyo opens her box and finds the left glove, you instantly know that your box in London contains the right one. There is nothing spooky about this. No mysterious signal traveled faster than light between the boxes. The information, the right-handedness of your glove, was there all along, a pre-existing fact, a hidden variable determined the moment the gloves were separated. Einstein argued that entangled particles must be the same. Their seemingly coordinated behavior wasn't the result of some instantaneous ghostly connection, but of a shared set of instructions, a cosmic blueprint they were given at their moment of creation. The spin of one particle wasn't times becoming times up, and times causing times the other to become down. They were times always times destined to be up and down respectively if measured along the same direction. We just didn't know it until we looked. The universe in this view remains local and sensible. Nothing travels faster than light. Everything has a definite state, even if we are ignorant of it. Quantum mechanics was simply incomplete, a statistical approximation of a deeper deterministic reality waiting to be discovered. For 30 years, this was where the argument stood, a stalemate, an unprovable assertion against an unsettling theory. You either believed in Einstein's hidden rulebook, or you believed in Bohr's spooky action. There was no experiment, no physical test that could distinguish between the two. Opening the box in London and the box in Tokyo and seeing a right and a left glove is an outcome that both theories could accommodate. One says the outcome was predetermined. The other says it was undetermined until the moment of observation. How could you ever prove which was right? It seemed an impossible task, a question forever locked away in the realm of metaphysics, until John Bell, in his spare time with paper and pen, forged the key. He devised something that would tear the question out of the abstract halls of philosophy and place it squarely onto the laboratory bench. It was not a grand new theory, nor a complex experiment. It was a piece of mathematics, an elegant, shockingly powerful argument known today as Bell's theorem, or more specifically, Bell's inequalities, and it would change everything. Bell's genius was to realize that while you couldn't distinguish the two theories by making a single type of measurement, you could expose the truth by introducing a bit of creative complexity. He shifted the focus from asking just one question of the particles to asking a series of different questions. It was this shift that would finally reveal the limits of any possible hidden variable theory. To understand the profound elegance of his thinking, let us step away from particles and imagine a far more human scenario. Picture two incredibly disciplined criminal suspects, Alice and Bob, who are partners in a grand conspiracy. They are captured and held in separate, completely isolated interrogation rooms, unable to communicate in any way. You, the chief detective, know they have been carefully prepared. Before being separated, they synchronize their stories, creating a shared, prearranged set of answers to any questions you might ask. This prearranged list of answers is their hidden variable program, just like the one Einstein imagined for his particles. Now you decide on a simple interrogation strategy. You have only 3 possible yes or no questions you can ask. Let's call them question A, question B, and question C. Perhaps A is, was the getaway car blue? B is, did you use the east exit? And C is, was the time after midnight? To keep them on their toes for each round of questioning, you and your partner will randomly choose which one of the 3 questions to ask Alice and Bob. Sometimes you'll both happen to ask question A. Other times you might ask Alice question A, while your partner asks Bob question B. The one unbreakable rule of their conspiracy is this: if they are ever asked the times same times question, they must give times opposite times answers to maintain their cover story. So if you both ask question A and Alice says yes, Bob must say no. This mirrors the perfect anti-correlation of entangled particles when their spin is measured along the same axis. So far so good. If you only ever ask the same question, you will always get opposite answers and you will learn nothing. You can't tell if they are magically communicating or just following their pre-arranged script, but here is where Bell's insight enters the interrogation room. What happens when you and your partner start asking different times questions? Let's analyze their pre-written script, their hidden variables. For any given round, their script must have a predetermined set of answers for all 3 questions. For example, one possible script could be, Alice's answers will be A equals yes, B equals no, C equals yes. Because they must always give opposite answers to the same question. Bob's script is therefore automatically fixed. A equals no, B equals yes, C equals no. This is just one of 8 possible scripts they could have agreed upon beforehand. Now let the interrogation begin. You and your partner randomly pick questions over and over again hundreds of times, and you meticulously record the results. You are especially interested in the rounds where you asked different times questions. For example, you ask Alice question A, and your partner asks Bob question B. Using their script of A equals yes, B equals no, C equals yes for Alice, and A equals no, B equals yes, C equals no for Bob, their answers would be Alice A equals yes and Bob B equals yes. In this case, their answers times agree asterisk. Let's try another combination. You ask Alice question B, and your partner asks Bob question C. Her answer is B equals no, his is C equals no. Once again, they agree. One more. You ask Alice question A, your partner asks Bob question C. Her answer is A equals yes, his is C equals no. They times disagree asterisk. John Bell sat down and did the simple, painstaking math. He considered all 8 possible pre-written scripts the suspects could have. He then calculated across all the possibilities how often Alice and Bob should give the same times answer when they were asked different questions. His logic was irrefutable, grounded in basic probability. He found that if Alice and Bob were operating from any kind of pre-programmed local script, any set of hidden variables, then the number of times their answers agreed had to be times greater than or equal to times the number of times they disagreed in certain combinations. He worked out a precise mathematical limit. He proved with absolute certainty that for any local predetermined reality, the correlations between their answers could not exceed a specific threshold. This threshold, this boundary drawn by common sense and classical probability, is Bell's inequality. It was a line in the sand, a mathematical ultimatum delivered to reality itself. He was saying, if the world is the way Einstein believed it is, then the results of this experiment must obey this rule, period. But then came the twist, the final staggering blow to classical intuition. Bell then turned to the strange mathematics of quantum mechanics itself. He asked the same question not of 2 suspects, but of 2 entangled particles. What does the established quantum formalism predict for the correlations when we measure their properties, their spin along 3 different angles, angle A, angle B, and angle C? He ran the numbers, and the prediction that emerged from the quantum equations was breathtaking. Quantum mechanics predicted that the entangled particles would show a level of coordination stronger times than Bell's limit. They would agree with each other more often than any pre-programmed local hidden variable theory could possibly allow. The theory of quantum mechanics predicted in stark, unambiguous terms that reality would violate Bell's inequality. The implication was earth-shattering. It was as if our 2 suspects, Alice and Bob, were able to coordinate their answers to a degree that was logically impossible for any pre-written script. It's as if when you ask Alice question A, she somehow knows which question you are asking Bob, B or C, and adjusts her answer accordingly, instantly, and without any physical connection. The quantum prediction suggested a universe where the 2 particles were not 2 separate things carrying shared memories, but were somehow still a single unified system no matter how far apart they flew. Their connection wasn't a memory of the past, it was a living, active link in the present. Bell's theorem didn't prove that quantum mechanics was right. It did something far more important. It proved that Einstein's worldview and Bohr's worldview gave fundamentally different times, experimentally testable times, predictions about the nature of the universe. Suddenly, the decades-old debate was no longer philosophical. John Bell had transformed it into a concrete physical question. He had forged a mathematical scalpel sharp enough to dissect reality itself. He had provided the blueprint for an experiment that could act as the ultimate arbiter. The choice was now terrifyingly clear. You could build a device, generate pairs of entangled particles, and measure their properties along different randomly chosen angles over and over again. You would then count the correlations. If the results obeyed Bell's inequality, it would mean Einstein was right. Reality is local. The particles do carry hidden instructions. And quantum mechanics, for all its success, is an incomplete theory. It would mean that a deeper, more intuitive reality lies beneath the quantum veil waiting to be discovered. But if the experimental results times Bell's inequality, if they matched the predictions of quantum mechanics, the consequences would be far more profound. It would mean that Einstein was wrong. It would mean there are no hidden variables. It would mean that our universe is fundamentally non-local. It would prove beyond any shadow of a doubt that two particles separated by vast distances can be linked by a connection that defies our classical understanding of space and time. That the measurement of one particle here can have an instantaneous, unmitigated effect on its partner over there. Spooky action at a distance would be stripped of its metaphorical quotation marks and shown to be a hard, undeniable fact of the cosmos. The philosophical fog had been burned away by the harsh light of mathematics. The confrontation that Einstein and Bohr had started in the 1,930 seconds was now set to be concluded not with arguments, but with data. Bell had thrown down the gauntlet. Now all that was needed was an experimentalist brave enough to pick it up. A new generation of physicists would have to rise to the challenge to build the machines that could ask nature this ultimate question and finally force it to show its hand. The stage was set for one of the most pivotal experimental showdowns in the history of science. And so Bell's theorem was no longer just ink on paper. It had become a ghost story written in the language of mathematics, a chilling proposition that reality itself might be haunted. For decades, the debate between Einstein and Bohr had raged in the hallowed halls of physics, a battle of philosophical titans. Einstein, with his deep, intuitive faith in a sensible, orderly cosmos, insisted that if you measured something here, it could not instantaneously affect something over there. This was his principle of local realism, a cosmic anchor holding the universe to the laws of cause and effect we see every day. Bohr, on the other hand, championed a quantum world that was fundamentally probabilistic, interconnected, and profoundly strange, a place where our classical intuitions simply broke down. Bell's inequality transformed this grand debate from a matter of opinion into a question with a definitive, measurable answer. He had drawn a line in the sand of space-time. On one side lay Einstein's universe, familiar, predictable, and local, where any correlations between distant particles must be explained by hidden information they carried with them from their creation, like two identical letters sealed in envelopes and sent to opposite ends of the Earth. On the other side lay the quantum universe of Bohr, a bizarre realm of instantaneous connection where our entangled particles remained part of a single unified system, no matter the distance, their fates linked by a ghostly handshake that defied space itself. The inequality was the referee. It set a statistical limit on the correlations you could ever hope to find in a local realist universe. If experiments showed correlations that exceeded Bell's limit, then Einstein's cherished worldview, the very bedrock of classical physics, would be shattered. All that was needed was someone with the courage, the ingenuity, and perhaps the sheer audacity to put reality itself on trial. That person was a young postdoctoral researcher at Berkeley in the late 1960s, a physicist named John Clauser. At the time, the foundations of quantum mechanics were considered settled, a subject for philosophers, not for serious, ambitious scientists looking to build a career. To even consider testing Bell's theorem was seen as a professional dead end, a fool's errand chasing after philosophical phantoms. But Clauser was captivated. He saw what few others did, that this was not just philosophy. This was the most profound experimental question one could possibly ask. Is the universe as strange as quantum mechanics claims it is? He, along with his colleagues Stuart Friedman, Michael Horn, and Abner Shimony, adapted Bell's abstract inequality into a concrete experimental proposal, something that could with great difficulty be built in a laboratory. It was a gamble, a leap into the intellectual abyss. Imagine his lab in the early 1972. This was not a grand state-of-the-art facility. It was a cobbled-together affair, a testament to pure scientific will, built with scavenged parts, borrowed equipment, and boundless determination. The heart of the apparatus was a cascade of excited calcium atoms. When these atoms relaxed, they didn't just emit one photon of light. They spat out two, in opposite directions like celestial twins birthed from a single quantum event. Crucially, these photons were entangled. Their polarizations, the orientation of their light waves, were linked in a delicate quantum dance. According to quantum mechanics, while each individual photon had no definite polarization, until it was measured, their relationship was absolute. If you measured one and found it to be vertically polarized, you would know in that exact instant that its twin, now meters away and speeding off in the opposite direction, was also vertically polarized. On either side of the atomic source, Clauser placed a polarizing filter like the lenses in a pair of sunglasses, followed by a sensitive photon detector. He could rotate these filters to any angle he chose. Think of this as asking each photon a question. Are you vertically polarized, or are you polarized at a 30-degree angle? The photon's answer was a simple yes or no. It either passed through the filter and was counted by the detector, or it was blocked. Einstein's local realism predicted a simple common-sense outcome. The photons, he would argue, must have left the calcium atom with a predetermined set of instructions, a hidden genetic code that dictated how they would respond to any filter at any angle. The correlations between the pairs would be strong, yes, but they would never ever exceed the statistical limit set by Bell's inequality. The universe in its heart was playing with honest dice. For 2 years, Clauser and Friedman ran the experiment. The data trickled in photon by photon, a slow, meticulous accumulation of evidence. Each click of the detector was a vote, a single ballot cast in a cosmic election to decide the nature of reality. You can feel the tension in those quiet hours, the weight of the question hanging in the air. Was Einstein right? Was there an elegant hidden order beneath the quantum chaos? Or was the universe truly held together by this spooky action at a distance? Finally, they had enough data to make the call. They plotted the results, comparing the correlations they measured at different angles of the polarizers against the rigid boundary set by Bell's theorem. The result was a shockwave. The data points didn't just land on Bell's line, they soared past it. They violated the inequality, and not by a small margin but by 5 standard deviations, a result of overwhelming statistical significance. The ghostly handshake was real. The universe was playing with dice that seemed impossibly to be influencing each other from across the room faster than the speed of light. Clauser had stared into the abyss, and the abyss had revealed a profoundly interconnected reality. Einstein, it seemed, was wrong. But in science, a single result, no matter how dramatic, is never the final word. The scientific community, steeped in the classical intuition of centuries, was skeptical. They pointed to potential loopholes, subtle ways that Einstein's local universe could still be masquerading as a quantum one. Perhaps the experiment wasn't perfect. The most significant of these was the locality loophole. What if critics argued the 2 detectors, the 2 measurement devices, were somehow communicating with each other? What if when the first filter measured its photon, it sent a secret signal at or below the speed of light to the other side, telling the second filter how to orient itself? Or telling the second photon how to behave? Clauser's experiment was static. The filters were set in place and left there for long periods. There was, in theory, plenty of time for some unknown conventional signal to coordinate the results and create the illusion of non-locality. To truly slam the door on Einstein's worldview, you would have to make your measurement choices so blindingly fast that no conceivable message, not even one traveling at the speed of light, could possibly bridge the gap in time. The challenge was immense. It required a level of technological sophistication and speed that was in the 1,000 970 seconds at the very edge of what was possible. Across the Atlantic in a laboratory near Paris, a French physicist named Alain Aspect took up this monumental challenge. His goal was not merely to replicate Clauser's result, but to assassinate the loopholes. Aspect designed a series of increasingly brilliant and refined experiments throughout the late 1970 seconds and early 1980 seconds, culminating in a masterpiece of experimental design. His photon source was far more efficient, producing a steady, reliable stream of entangled pairs, but his true innovation, the device that would become legendary, was his switch. He placed his photon detectors much farther apart, about 12 meters. And in the path of each photon, he engineered an ultra-high-frequency acoustic optical switch. This device could change the path of a photon, directing it to one of two different polarizers set at different angles. And it could make this switch in mere nanoseconds, billionths of a second. This is the critical part. The choice of which polarizer would measure the photon was not made until long after the entangled photons had left their source and were already in flight. The distance between the two switching devices was so great, and the switch itself was so fast, that by the time one photon was measured at one end, there was simply not enough time for any information about that measurement, what angle was chosen, what the result was, to travel 12 meters and influence the measurement of its twin. Light itself, the universe's ultimate speed limit, could not cross that divide in time. It was like two interrogators in separate soundproof rooms deciding what question to ask their respective suspects only a fraction of a second before they burst through the door. There could be no coordination, there could be no conspiracy. If Bell's inequality was still violated under these extreme conditions, it would be the death knell for local realism. The experiment was a marvel of precision engineering. As it ran, it was effectively asking the universe the same question as Clauser, but now with an unassailable rigor. Are you local or are you non-local? Once again, reality cast its vote. Photon by photon, the data accumulated, painting a picture of the world at its most fundamental level. The results were breathtaking. Aspect and his team found that the quantum correlations persisted as strong and undeniable as ever. The violation of Bell's inequality was clear, stark, and unambiguous. Even when the universe had no time to cheat, the spooky connection held firm. The ghostly handshake reached across space-time, its grip instantaneous and unbreakable. The locality loophole was slammed shut, bolted, and sealed. For most of the physics community, this was the final conclusive proof. The strange, beautiful, and deeply counterintuitive world described by quantum mechanics was not just a useful mathematical tool. It was real. We lived in a non-local universe. Yet even after Aspect's triumph, a final, almost philosophical phantom remained. It was a loophole so vast and so strange that most physicists considered it a sign of desperation, but it could not be dismissed out of hand. It was called the freedom of choice loophole, or sometimes superdeterminism. It proposed a conspiracy of cosmic proportions. What if it suggested the choices made by the experimenters, Clauser turning his dial, Aspect's random switch firing, were not truly free? What if the state of the entangled particles and the settings of the detectors were both predetermined by some common cause far back in their shared history? What if the universe had been rigged from the very beginning, from the moment of the Big Bang itself, to produce these specific correlations? In this scenario, the particles don't need to communicate because their properties and the questions we would ask them were already written into the fabric of creation 13.8 billion years ago. It was a mind-bending idea, a universal puppet show where our apparent free will was just part of the script, all designed to create the illusion of quantum spookiness. How could you possibly design an experiment to rule out a conspiracy that began with the birth of time itself? You would need a choice maker, a random number generator, so ancient, so distant, so causally disconnected from your laboratory that no conceivable physical process could have coordinated it with the particle source on Earth. You would need to reach out into the cosmos itself. This was the grand vision of Anton Zeilinger, an Austrian physicist who had become a master of orchestrating these fundamental quantum tests. Working with a global team of collaborators, Zeilinger conceived of the ultimate Bell test, one that would use the universe as its own random number generator. They set up their experiment, an exquisitely refined version of Aspect's apparatus, with entangled photon pairs being sent to detectors in Vienna. The crucial difference was in how the measurement settings were chosen. The team pointed 2 telescopes at the night sky, each aimed at a different, incredibly distant quasar. Quasars are the blazing cores of ancient galaxies, powered by supermassive black holes, some of the oldest and most luminous objects in the universe. The light from these cosmic beacons has been traveling towards us for billions of years, a stream of photons that left their source long before the Earth or even our Sun had formed. Here was the genius of the experiment. The instant one of these ancient photons arrived at one of the telescopes, its properties, specifically its color, whether it was redder or bluer than a certain average, would be used to make a random choice. That choice would then determine the setting for the corresponding polarizer in Vienna, the question that would be asked of the entangled earthly photon. Because the 2 quasars were in completely different parts of the sky, the light arriving from them at any given moment had been causally disconnected for almost the entire history of the universe. One quasar was 7.8 billion light-years away, the other 12.2 billion. There was no way the quasar on the right could know what the quasar on the left was doing. There was no way the particle source in the lab could have conspired with a signal that left its source billions of years before our planet existed. This was it, the final stand. The ancient light of the cosmos would serve as the ultimate impartial witness, its random fluctuations providing the final unassailable choice in the long trial of reality. In 2017, the cosmic Bell test was performed. For hours under the night sky, the experiment ran. Entangled particles created in a Vienna laboratory had their fates decided by light that had traveled through the void for eons. The scale of it is almost impossible to comprehend. We were weaving together the impossibly small with the unimaginably vast, the fleeting existence of a quantum particle with the deep ancient history of the cosmos. The data came in, the correlations were calculated, and the result was a thunderous confirmation. Even with the universe itself choosing the questions the strange quantum connection held, Bell's inequality was violated by a staggering degree. The final loophole, the grand cosmic conspiracy, was sealed forever. The verdict was in, delivered not by human hands but by the stars themselves. Reality is non-local. The journey was over. From a thought experiment born in the mind of Albert Einstein, to a mathematical challenge from John Bell, to the heroic decades-long efforts of Alain Aspect Zeilinger and hundreds of other scientists, we had interrogated the universe. At its most fundamental level, we had asked it the most profound question we could frame, and it had answered. The world is not as it seems. Beneath the solid, predictable reality of our everyday lives lies a seething, interconnected quantum realm where space is no barrier and connection is instantaneous. We had proven that the ghost in the machine was real. This discovery was no longer a matter of philosophical debate. It was now an established fundamental principle of our universe, as real as gravity, as certain as the speed of light. The question was no longer time's, if time's spooky action at a distance was real. The question, the one that would ignite the next great technological revolution, was what could we now do with it undefined? The echoes of the final experiment fade. The data, cold and irrefutable, has been gathered from laboratories across the world, each one a nail in the coffin of a simple local reality. We have followed the evidence, peered into the subatomic realm, and have been forced to accept a truth that defies every intuition we hold dear. Entanglement is not a ghost, not a statistical fluke, nor a misunderstanding. It is a fundamental feature of our universe. But with this acceptance, the ground beneath our feet doesn't solidify. Instead, it dissolves into a profound and unsettling abyss of new questions. In proving the connection real, we haven't found a final answer. We have simply unlocked a door to a far deeper and more mystifying chamber of existence. Here in this new territory, the paradoxes don't just multiply, they mature. The most immediate and alarming of these seems to be a direct assault on the absolute bedrock of modern physics, a pillar erected by Einstein himself, the cosmic speed limit. Nothing we have been taught can travel faster than light. It is the ultimate law of the road for the universe, the principle that keeps causality intact, ensuring that an effect can never precede its cause. Yet we have just witnessed a phenomenon where the measurement of a particle in one corner of a laboratory appears to have an instantaneous consequence on its entangled twin, even if that twin were on the far side of the galaxy. It seems like a blatant violation, a cosmic crime committed in plain sight. Does this mean our understanding of space-time is fundamentally broken? Can you, by simply tickling a particle here on Earth, truly send a signal to a starship orbiting Proxima Centauri in the same moment, shattering the very fabric of particle relativity? The answer, astonishingly, is no, and the reason reveals a subtlety in the quantum world that is as elegant as it is frustrating. Nature, it seems, has built a perfect firewall. This safeguard is known as the no communication theorem, a principle that prevents this spooky connection from ever being harnessed for faster-than-light communication. Imagine you and a distant friend each hold one of two entangled particles, say with the property of spin. Before measurement, each particle is in a superposition of both spin up and spin down. When you measure your particle, you might find it to be spin up. Instantly, you know your friend's particle, no matter how far away, has collapsed into the spin-down state. You know this with absolute certainty. The spooky action has occurred, but here is the crucial twist. You had absolutely no control over your outcome. You could not force your particle to be spin-up. The result was completely, utterly random. For you, it was a 50-50 chance, like the flip of a fair coin. Your friend measuring her particle also gets a completely random result. A 50-50 chance of spin down. There is no information in her measurement alone. It's just noise. She has no idea that you have even made a measurement, let alone what result you got. The only way for the two of you to see the perfect anti-correlation to confirm that when you got heads she got tails is to communicate your results later. You would have to pick up a phone or send a radio signal or travel to meet her, all methods that are strictly limited by the speed of light. The correlation is real, the connection is instantaneous, but information, the meaningful, controllable pattern you would need to send a message, remains a prisoner of Einstein's law. It's a maddening paradox. The universe possesses a cosmic switchboard with instantaneous connections, but it has disabled all the telephones. It allows for a perfect shared knowledge between distant points in space-time, but it forbids us from using that knowledge to have a conversation. This firewall saves causality. It ensures you cannot send a message back in time, a possibility that would arise in certain frames of reference if faster-than-light signaling were possible. Physics, as we know it, is safe from the temporal chaos of shattered cause and effect. Yet this very solution plunges us into an even deeper philosophical crisis. If the connection isn't transmitting information, if it isn't a thing in the classical sense moving from point A to point B, then what on earth is it? What does this silent, instantaneous correlation tell us about the nature of reality itself? This is where the true vertigo begins. For centuries, our physics was built on two foundational common sense assumptions. The first is locality, the idea that an object is only directly influenced by its immediate surroundings. For something over there to affect something over here, a force or a field or a particle must travel the intervening distance. The second is realism, the intuitive belief that objects have definite pre-existing properties, whether we are looking at them or not. A planet has a specific position in its orbit even when no telescope is pointed at it. A chair exists in your living room solid and defined even when you are not in the house. Quantum entanglement forces us to confront an earth-shattering choice, an ultimatum delivered by the universe itself. The experiments confirming Bell's theorem have proven beyond any reasonable doubt that you cannot have both. At least one of these cherished foundational pillars of our worldview must fall. If you choose to abandon locality, you accept what we have just seen, a universe that is profoundly interconnected, where a measurement performed here can be inextricably and instantly linked to an outcome in a distant galaxy. In this view, the two entangled particles are not separate entities that somehow influence each other across space. Instead, you must think of them as a single, unified system, one irreducible whole that just happens to be manifested in two different locations. Measuring one part of the system provides you with knowledge about the other part not because a signal traveled between them, but because they were never truly separate to begin with. The concept of distance itself, in some deep and mysterious way, seems to become irrelevant for this single quantum object. This idea of non-locality is jarring. It suggests a hidden layer of reality, a holistic web of connection that lies beneath the surface of the separated, isolated objects we perceive in our everyday lives. It paints a picture of a cosmos that is not a collection of individual things, but a single, sprawling, interconnected entity. But what if you find that possibility too much to bear? What if you try to save locality by sacrificing realism instead? This path leads to an even more radical conclusion about the world. To give up realism is to accept that the properties of a particle, its spin, its polarization, its position, do not exist in any definite state until the very moment of measurement. Before you look, the particle is not spin up or spin down. It is a cloud of pure potential, a mathematical wave of probability described by the Schrödinger equation. The act of measurement itself is what forces the universe to make a choice to actualize one specific reality from a ghostly menu of possibilities. In this view, the universe is not a static stage where we are merely observers discovering what is already there. Instead, our very act of observation becomes a participatory creative act. We are not just uncovering reality, we are in a limited but profound way helping to bring it into being. The correlation between entangled particles arises not because they had secret prearranged instructions, but because the act of measuring one instantly defines the context for the measurement of the other, forcing both to crystallize out of the fog of potential in a perfectly correlated way. This forces us to re-examine the very nature of causality. Does measuring particle A times cause times particle B to snap into a specific state? The word cause feels wrong-laden with our classical intuitions of billiard balls knocking into one another. The quantum connection is something more subtle, more ethereal. There is no force, no energy exchange. It's more akin to a logical implication that transcends space. If you know that two twins always wear opposite colors, seeing one in a white shirt doesn't times cause times the other to wear a black one. It simply reveals the state of the entire pre-correlated system. But with entanglement, this correlation is forged in a realm of pure potentiality and revealed across space-time. It's a form of causality without a mechanism. We can visualize a relationship without a physical messenger. This has led some physicists to suggest our very concepts of cause and effect, so useful in our macroscopic world, may simply be inadequate tools when we descend to the fundamental level where space and time themselves become less distinct. Entanglement thus becomes the most dramatic and unsettling expression of a core mystery at the heart of quantum mechanics, the measurement problem. Why does the act of observation have this seemingly magical power to collapse a wave of infinite possibilities into a single concrete reality? For a single particle, this is already a profound puzzle, but for an entangled system, the puzzle is stretched across the cosmos. When you measure one particle, you are not just collapsing its own wave function, you are instantaneously collapsing a shared distributed wave function that might span light years. The observer, so long considered a passive element in science, is dragged to center stage. Their role in shaping reality suddenly and uncomfortably amplified. It suggests that consciousness, or at least the interaction between a complex measuring device and a quantum system, is not incidental to the universe. It is a critical part of the process by which the potential becomes actual. Faced with this stark choice between our most basic intuitions, physicists themselves are deeply divided, wrestling with these implications in a debate that has raged for nearly a century. The traditional Copenhagen interpretation, favored by Niels Bohr, essentially advises us not to ask what is real before a measurement is made. It posits that physics is only about predicting the outcomes of experiments, and that any attempt to describe a deeper, unobserved reality is meaningless speculation. It embraces the weirdness as fundamental a feature of the world we must simply accept without a classical explanation. For Bohr, the non-local connection was a simple fact of the quantum formalism, not a ghost to be explained away. Other interpretations have been born from a deep dissatisfaction with this shut-up-and-calculate approach. The many-worlds interpretation, for example, makes a radical attempt to preserve both realism and locality. It suggests that a measurement doesn't collapse the wave function at all. Instead, every possible outcome of a measurement actually happens, each one branching off into its own parallel universe. When you measure a particle as spin-up, another version of you in another universe that just split away from yours measures it as spin-down. In this view, the entangled correlation is preserved across the multiverse. The connection isn't spooky action at a distance. It's a perfectly local event where your measurement here reveals which branch of reality your distant partner now inhabits. It saves locality, but at the staggering cost of an infinite and ever-growing number of parallel worlds. Then there are hidden variable theories like Bohmian mechanics which stubbornly hold on to realism. They propose that particles do have definite properties and positions at all times, guided by a hidden pilot wave. In this picture, entanglement is real, and the theory is explicitly non-local. The pilot wave connects the two particles, acting as a kind of instantaneous information field that guides their behavior. It gives us back our concrete reality, but forces us to accept a holistic, non-local universe in its rawest form, a vision that Einstein himself, despite his quest for realism, could never bring himself to endorse. The fact that brilliant minds can look at the same experimental results and arrive at such wildly different, almost metaphysical conclusions, from refusing to speak of deep reality to invoking infinite universes to positing hidden pilot, waves is a testament to the sheer paradigm-shattering power of entanglement. It tells us that we are not just tidying up the loose ends of a known theory. We are standing at the edge of a conceptual chasm. These paradoxes, then, are not failures of the theory. They are its most potent revelations. They are the cracks in our classical worldview, and through those cracks we are beginning to glimpse a deeper structure of the cosmos. The instantaneous connection of entanglement, this perfect choreography that mocks distance, might not be a violation of the cosmic order, but rather a clue to its true nature. It suggests that at the most fundamental level, the universe may not be a collection of tiny separate bits of matter scattered through empty space. Instead, it might be an indivisible whole, where the concepts of separation and distance are emergent properties, illusions that belong to our macroscopic scale. Perhaps space itself is not the fundamental container of reality, but rather a construct, a network of relationships derived from these more primary quantum connections. This is the frontier. We have verified the spooky action, and we have shielded relativity from its apparent threat. Now we are left to grapple with what it all means. These unresolved tensions, these philosophical battles being waged on the blackboards of theoretical physicists, are not signs of a theory in crisis. They are the growing pains of a scientific revolution. They are the signposts pointing the way forward, urging us to search for a new principle, a more unified theory that can perhaps explain both the rigid structure of Einstein's space-time and the wild, holistic interconnectedness of the quantum world. A theory in which entanglement is not a paradox to be explained away, but a foundational clue to the ultimate nature of everything. The questions it raises about reality, causality, and our place as observers within the cosmos are perhaps the most important questions we can ask, and the search for those answers is what will drive the next great leap in our understanding of the universe. And so the ghost that haunted Einstein, the perplexing phantom that defied a century of our most cherished intuitions about reality, was finally cornered, not to be exercised but to be understood. We have travelled through the disorienting looking glass of quantum mechanics, followed the breadcrumbs of light through double slits, and stood at the precipice of Bell's theorem, where the universe itself declared its verdict. The connections are real. The spookiness is woven into the very fabric of existence. For generations, this was the end of the story, a profound, unsettling, and ultimately philosophical victory, a chapter closed on the nature of what is. But for a new generation of pioneers, this was not an ending. It was a key that didn't just unlock a deeper understanding of the cosmos, but a key that could be turned. The question that once echoed in the halls of physics, what does it mean, was being replaced by a far more audacious and electrifying one. What can we build with it? We stand now at that threshold, moving beyond the debate and into the laboratory, shifting our focus from the astonishment of discovery to the architecture of revolution. The spectre of entanglement is about to be put to work. The first blueprints for this new world are drawn on the canvas of computation. For all their power, the machines that define our modern era, the silicon hearts of our civilization, are profoundly classical. They are masters of logic, but a very specific, rigid logic. At their core, they operate on a simple, unambiguous principle: the bit, a 1 or a 0, a current flowing or a current stopped, a light switch that is definitively on or definitively off. This binary system, scaled to billions and trillions of operations per second, has granted us immense power. It has mapped our genome, predicted our weather, and connected our world, but it has limits. There are entire classes of problems, vast domains of unimaginable complexity, where this binary approach fails. These are not problems of speed, but problems of possibility. Simulating the intricate dance of atoms in a new drug molecule, optimizing global logistics on an impossibly vast scale, or factoring numbers so large they form the very foundation of our digital security. For these challenges, a classical computer, no matter how powerful, is like trying to describe a symphony using only 2 notes. It would take our fastest supercomputers longer than the age of the universe to even begin to untangle such complexity. The universe, however, solves these problems effortlessly every single moment. The folding of a protein, the process of photosynthesis, these are quantum computations happening all around us. To solve them ourselves, we needed to learn to speak the universe's native language. We needed a new kind of switch. Enter the qubit, the quantum bit. Unlike its classical cousin, a qubit is not limited to a simple on or off state. Harnessing the principle of superposition, it can exist as a 0, a 1, or a delicate probabilistic blend of both simultaneously. It is not a light switch, but a dimmer, able to occupy every possible position between darkness and light all at once. This alone is a profound leap, granting a single qubit access to a richer spectrum of information. But the true revolution ignites when we take these qubits and entangle them. When 2 qubits are linked, they cease to be independent entities. They become a single unified system, described by a single quantum state. Add a third, and the system grows more complex. A fourth, and its potential expands exponentially. With just a few hundred entangled qubits, we can create a computational space so vast it could hold more numbers than there are atoms in the known universe. This is not just a faster computer, it is a fundamentally different kind of reality. A classical computer checks possibilities one by one, a relentless but linear march through a maze. A quantum computer, by existing in all possible states at once, explores every path through the maze simultaneously. It is an oracle of probability, capable of seeing the entire landscape of a problem in a single holistic glance. To build such a machine is to build a cathedral of precision, a sanctuary shielded from the noisy intrusions of the outside world. The processors themselves, intricate webs of superconducting circuits or lattices of trapped ions, must be cooled to temperatures colder than deep space, just fractions of a degree above absolute zero. In this profound stillness, the delicate quantum states can be maintained, manipulated by exquisitely timed pulses of microwave radiation and laser light. Here, in these isolated chambers of extreme cold and quiet, we weave the threads of entanglement, coaxing particles into that mysterious non-local embrace. The slightest vibration, a stray photon, a wisp of thermal energy can shatter the spell. This is the great enemy of the quantum engineer: decoherence. It is the universe trying to look at our calculation, forcing our shimmering cloud of possibilities to collapse into a single mundane classical answer. The struggle to build a fault-tolerant quantum computer is a heroic battle against the universe's own intrinsic curiosity. It is a quest to build a bubble of pure quantum reality and hold it long enough to ask it a question it alone can answer. And the answers we seek will redefine our world. Imagine designing new catalysts that can pull carbon from our atmosphere with perfect efficiency, or creating novel medicines by simulating their exact interaction with our bodies at the subatomic level. Imagine discovering new materials for lossless energy transmission, or developing artificial intelligence that can learn and reason in ways we can barely conceive. These are the promises whispered from within the quantum realm, the problems that await their entangled oracle. But as with every great technological leap, a new power brings a new peril. The very same quantum algorithms that promise to design miraculous drugs could also shatter the foundations of our digital world. The encryption that protects everything from our bank accounts and government secrets to our private communications is largely built on a simple mathematical trick. It's incredibly difficult to find the prime factors of very large particle numbers. For a classical computer, this task is practically impossible. But for a sufficiently powerful quantum computer using an algorithm devised by Peter Shaw, it becomes trivial. The digital locks that secure our civilization could be broken open in a matter of hours. The quantum revolution, it seems, poses a threat to the very world it seeks to improve. Yet in a moment of beautiful cosmic symmetry, the ghost in the machine provides its own shield. The same principle that empowers the codebreaker can also create the ultimate code. The solution to the quantum threat is more quantum mechanics. This leads us to the second great application of entanglement, a new form of communication, one secured not by mathematical complexity, but by the fundamental laws of physics. It is called quantum cryptography. Imagine two individuals, let's call them Alice and Bob, who wish to share a secret key to encrypt their messages. Instead of sending the key as a string of classical bits, they send it using a stream of entangled photons. Alice creates pairs of entangled photons and keeps one of each pair while sending the other to Bob. They are now linked by their shared quantum connection. To form the key, they both measure a property of their photons, like their polarization. Because their particles are entangled, Alice's measurements will be perfectly correlated with Bob's. If her photon is measured as vertically polarized, she knows instantly that his is as well. By repeating this process, they build a shared random string of ones and zeros that can be used as an unbreakable one-time encryption key. Now consider an eavesdropper, Eve. If Eve tries to intercept and measure the photons traveling from Alice to Bob, her very act of observation will irrevocably disturb their quantum state. The moment she looks at a photon, she breaks the delicate thread of entanglement that connects it to its partner. When Alice and Bob later compare a small sample of their measurements over a public channel, they will immediately notice discrepancies, a telltale signature of noise and error where there should be perfect correlation. The ghost has been disturbed. They will know with absolute certainty that their line is not secure. They can discard the compromised key and begin again. This is not a security system that is merely difficult to crack. It is one where any attempt at eavesdropping is instantly and unavoidably revealed. The universe itself acts as the ultimate sentinel, its laws guaranteeing that the secret remains a secret or the attempt to steal it is exposed. It's a cosmic tripwire woven from spooky action at a distance. Already this technology is moving from the laboratory into the real world. Secure quantum communication networks are being built, linking cities with fiber optic cables that carry not just data, but the promise of perfect privacy. Satellites are now being used to beam entangled photons across continents, creating the first nodes of a global, unhackable quantum internet. This is a network where the security of a financial transaction, a state secret, or a private conversation is guaranteed by the same physical principles that govern the heart of a star and the nature of reality itself. We are building a new layer of communication atop our existing infrastructure, a quantum layer where secrets are not just hidden, they are sanctified by physics. But this global network hints at an even more mind-bending possibility, one that seems torn from the pages of science fiction. The ability to transmit not just a secret key, but the very essence of a quantum state from one point to another instantaneously without it ever crossing the space in between. This is the domain of quantum teleportation. Before you imagine shimmering beams of light and the deconstruction of matter, we must be precise. We are not teleporting physical objects. We cannot beam a person from one place to another. What we are teleporting is far more subtle and in many ways far more profound information. The complete, perfect, and infinitely delicate quantum state of a particle. It works like this. Imagine Alice has a particle, let's call him Charlie, whose quantum state she wants to teleport to Bob, who is miles away. Alice also possesses one particle from an entangled pair, while Bob holds the other. The two are inextricably linked across the distance. Alice then performs a special kind of joint measurement on her particle, Charlie, and her half of the entangled pair. This measurement does two things. First, it instantly projects Bob's particle into a state related to Charlie's original state. Second, it destroys the original state of Charlie. The no-cloning theorem of quantum mechanics forbids making a perfect copy. The information cannot exist in two places at once. The original must be sacrificed for the teleported version to be born. Alice is left with two pieces of classical information from her measurement, just a couple of bits. She sends these bits to Bob through a conventional channel like a radio signal or an email. When Bob receives this classical information, it acts as a set of instructions. It tells him exactly which of a few specific operations like a flip or a rotation to perform on his entangled particle. He applies the correction, and in that instant his particle transforms into a perfect identical replica of Alice's original particle Charlie. Think about what has just happened. The complete quantum description of Charlie, his superposition, his phase, everything that made him unique vanished from Alice's location and reappeared at Bob's. The information did not travel across the intervening space. The quantum connection, that ghostly entangled link, served as the conduit. The transfer of the state itself was instantaneous, a non-local leap across space-time. While Bob had to wait for Alice's classical instructions to arrive at the speed of light to complete the process, the quantum part of the information was already there. This is more than a parlor trick. It is the fundamental protocol for a future quantum internet, a network where quantum computers separated by continents can be linked together. A quantum processor in London could run a subroutine on a processor in Tokyo, sharing qubits as if they were in the same room. Data could be transferred with perfect fidelity, immune to the noise and degradation that plagues classical signals. This is the technology that will allow us to build distributed quantum sensors that could act as a single planet-sized telescope or create networks so secure and powerful they could simulate entire economies, ecosystems, or even quantum universes within themselves. We have taken the most bizarre and counterintuitive feature of reality and engineered it into a tool for communication. We have turned a spooky paradox into a practical post office for the quantum world. From the computational power that mirrors the universe's own complexity, to the cryptographic shield forged from the laws of physics, to the instantaneous transfer of information across empty space, the applications of entanglement are not merely incremental improvements. They are the seeds of a new technological epoch. We are standing at a precipice similar to that of our ancestors, who first learned to harness electricity. They saw it as a curiosity, a force of nature that could create sparks and twitch a frog's leg. They could not have envisioned the global electrical grid, the glow of cities at night, or the digital consciousness of the internet that would grow from it. We are in that same moment of dawning comprehension now. We have learned to control the spark of entanglement. We have built the first clumsy machines that can weave and manipulate its ghostly threads. What we have achieved is astounding, but it is nothing compared to what is to come. We have spent a century staring into the quantum abyss, wrestling with its meaning. Now we have reached in and we have pulled out the tools to build a new reality. The age of harnessing the spookiness has begun. And as we build this future, we must wonder, as our technology becomes ever more entangled with the quantum world, how will we ourselves be changed by it? And so we arrive at the end of one journey only to find ourselves at the threshold of 1,000 more. We began with a profound sense of unease, a deep and unsettling tremor in the very foundations of reality, first articulated by the brilliant mind of Albert Einstein. His discomfort was not born of ignorance, but of a fierce, passionate devotion to a comprehensible universe. He gifted us the language of our cosmic descent, coining that immortal phrase, spooky action at a distance. It was a dismissal, a critique, a heartfelt plea for a universe that made sense, one where cause and effect were loyal neighbors, not instantaneous conspirators across unimaginable voids. For Einstein, reality was local. A thing is here, not there. To influence it, you must touch it or send something to touch it, a particle, a wave, a signal bound by the unbreakable speed limit of light. This was the bedrock of his intuition, the pillar of his magnificent theories. Entanglement was a ghost in his machine, a violation of this sacred principle. His thought experiments, particularly the famous EPR paradox he devised with Podolsky and Rosen, were not designed to prove quantum mechanics right, but to expose its absurdity. He imagined two particles born together and forever linked, flying apart to opposite ends of the galaxy. To measure one, he argued, was to instantaneously know the state of the other, to collapse its wave function faster than light could ever travel. This to him was not physics, it was telepathy, it was magic. A universe governed by such a phantom connection was in his view incomplete. There had to be something more, some hidden information, some local hidden variables carried by the particles themselves like secret instructions written before their journey began. The universe, he insisted, does not play dice, and it certainly did not engage in interstellar witchcraft. For decades, this debate raged not in laboratories but in the minds of physicists on the chalkboards of hallowed universities and in the passionate letters exchanged between the titans of science. It was Einstein versus Bohr, a clash of philosophies as much as physics. Bohr's camp argued for a radical new reality, one where our classical intuitions were simply baggage from a world of familiar scales. They countered that the particles were never truly separate individuals after their interaction. They remained a single unified system, a single mathematical description no matter the distance between them. To measure one was to measure the system as a whole. The spookiness, they claimed, was not in the universe but in our outdated language, in our stubborn insistence on seeing two separate things where reality saw only one. It was a schism that defined a generation, a seemingly unanswerable question hanging over the soul of science. Was reality truly as strange as the quantum equations suggested, or was there a deeper, more sensible layer hidden from our view? The question lingered a beautiful philosophical impasse. For a time, it seemed it might remain there forever, a topic for late-night debates, but beyond the reach of empirical testing. Science, after all, deals with what can be measured. How could you possibly design an experiment to test the philosophical assumptions of the universe itself? But then came the breakthrough, a moment of staggering intellectual clarity from the mind of John Stuart Bell. In 1964, he transformed the philosophical debate into a mathematical question. He devised a theorem, a brilliant inequality that acted as a referee in the grand contest between Einstein's local reality and Bohr's quantum weirdness. Bell's theorem was a gauntlet thrown down to nature itself. It made a concrete, testable prediction. If Einstein was right, if there were hidden instructions, then the correlations between measurements on entangled particles could only be so strong. There was a limit, a classical ceiling. But if Bohr and quantum mechanics were right, if the connection was truly instantaneous and non-local, then those correlations would be stronger. They would violate Bell's limit. Suddenly, the argument was no longer about intuition or philosophy. It was about numbers. It was about data. It was about building a machine asking nature a question with a clear yes or no answer, and having the courage to accept the outcome, no matter how profoundly it shattered our worldview. The stage was set for one of the most important experimental quests in the history of science, to put reality itself on trial. The subsequent experiments, from the early efforts of John Clauser to the definitive work of Alain Aspect and the loophole-closing masterpieces of Anton Zeilinger, were more than just technical achievements. They were interrogations of the cosmos. Each experiment was a refinement of the last, meticulously designed to eliminate any possibility of a classical explanation, to shut every door through which Einstein's hidden variables might sneak. They synchronized atomic clocks, used quasars from opposite ends of the universe to ensure the measurement settings were truly random, and separated detectors by vast distances. And with every new iteration, the verdict came back again and again with ruthless, undeniable clarity. Nature violated Bell's inequality. It violated it profoundly. The correlations were stronger than any local classical theory could ever permit. Einstein's cherished principle of locality, the intuitive idea that distant objects cannot instantly influence one another, was wrong. The ghost in the machine was real. The spooky action was not a paradox to be explained away. It was a fundamental feature of the universe we inhabit. There are no hidden instructions. The dice are not only played, they are linked. This was the moment the 20th century's greatest physics debate was finally settled. The world you experience every day, the solid, predictable world of cause and effect, is a grand illusion, an emergent property of a much deeper, of a much stranger reality. A reality woven together by these invisible, instantaneous, and unbreakable quantum threads. The confirmation of entanglement's spooky nature did not bring an end to the story. It was merely the end of the beginning. What was once a source of philosophical torment has, in a breathtaking turn, become one of the most powerful tools we have ever conceived. The very weirdness that so troubled Einstein is now the engine of a new technological revolution. We have moved from questioning entanglement to harnessing it. The same non-local connection that seemed to defy logic is now the foundational principle behind quantum computing. A classical computer bit is either a 0 or a 1, a simple switch that is either on or off. But a quantum bit or qubit can be both at once, a superposition of states. And when you entangle qubits, you create something extraordinary. You create a single complex computational entity. Changing one qubit instantaneously affects all the others. This allows a quantum computer to explore a vast landscape of possibilities simultaneously. For certain problems like factoring large numbers or simulating complex molecular interactions, this parallel processing offers an exponential leap in power. A problem that would take the fastest supercomputer billions of years to solve could in theory be conquered by a quantum computer in mere minutes. We are standing at the dawn of an age where we can design new medicines, molecule by molecule, create novel materials with unimaginable properties, and unlock the secrets of chemical reactions that govern everything from photosynthesis, industrial catalysts. We are building machines that think in the native language of the universe, a language of probability, superposition, and entanglement. The ghost in the machine is now becoming the architect of our future. Beyond computation, this spooky action is being woven into the fabric of our digital world to create a new paradigm of security. Quantum communication leverages entanglement to guarantee privacy in a way that is physically impossible to breach. Imagine sending a message encoded in the states of entangled particles. If an eavesdropper attempts to intercept and measure one of those particles, the act of measurement itself instantly alters the state of its entangled twin. The disturbance is immediate, a cosmic alarm bell that reveals the presence of a spy. This isn't just a better form of encryption. It is perfect encryption, with its security underwritten not by a clever algorithm, but by the fundamental laws of quantum physics. Financial transactions, government secrets, and personal data could one day be protected by a shield of non-locality, a private conversation held across a channel that spans space-time itself, a channel that nature itself forbids from being overheard, and the applications extend even to the realm of our senses. Entanglement is poised to redefine the limits of measurement. Quantum sensors using networks of entangled particles can achieve a level of sensitivity that classical devices can only dream of. We can build clocks so precise they would not lose a second in the entire age of the universe. We can create gravitational wave detectors capable of hearing the faintest whispers from colliding black holes. We can design medical imaging systems that can observe the delicate dance of biological processes within a single living cell without destroying it. We are learning to use these delicate quantum correlations as the ultimate probe, a way to see, to listen, and to touch the world with a finesse that was previously unimaginable. The spooky action that once seemed a flaw in the theory has revealed itself to be a feature of unparalleled utility, a cosmic resource waiting to be tapped. The philosophical unease of the 20th century has given way to the engineering challenges of the 21st, as we learn to build our world upon the very strangeness we once struggled to accept. Yet for all that we have explained, for all that we have harnessed, the deepest mysteries remain. The acceptance of entanglement has not closed the book on quantum mechanics. It has opened up entirely new volumes, filled with questions that are even more profound than the ones Einstein first posed. We now find ourselves looking at this phenomenon not just as a property of particles, but as a potential clue to the very structure of space-time and the nature of gravity itself. The two great pillars of modern physics, general relativity, our theory of the very large, and quantum mechanics, our theory of the very small, remain stubbornly incompatible. They speak different languages. But some of the most daring physicists today believe that entanglement might just be the Rosetta Stone we have been searching for. An electrifying idea known by the cryptic shorthand ER equals EPR suggests a stunning and profound connection. It proposes that entanglement between two particles EPR is in some deeper sense equivalent to a bridge in space-time, a wormhole connecting them. The spooky non-local link between particles is not just some abstract correlation, it is a manifestation of a literal geometric connection through the fabric of reality. In this view, space-time is not the fundamental stage on which the universe plays out. Instead, space-time itself is an emergent property stitched together by a vast, intricate network of quantum entanglement. The universe in this picture is a quantum circuit board of unimaginable complexity, and the geometry of space and the flow of time are simply the macroscopic patterns that arise from its underlying quantum connections. The force of gravity may not be a force at all, but a thermodynamic consequence of this entanglement geometry. This is a radical, mind-altering vision, one that suggests we have been looking at the universe inside out. We thought space contained entangled particles. Perhaps entanglement creates space. This leads us to an even more dramatic and speculative frontier, the holographic principle. This principle suggests that all the information contained within a volume of space, you, me, this planet, this entire galaxy, can be described by a theory that lives on the boundary of that space like a three-dimensional image projected from a two-dimensional surface. It is as if our familiar 3D reality is a grand hologram. And what is the mechanism for this projection? What stitches the hologram together? The leading candidate is once again quantum entanglement. The pixels on that distant two-dimensional boundary surface are a seething network of entangled qubits. The more entangled they are, the more space they project in the holographic interior. The connections we see as distance and geometry in our 3D world are in this view just a coarse-grained reflection of the intricate entanglement patterns on the boundary. This is where science touches upon the mythic. It is an idea that challenges our deepest assumptions about what it means to exist, to be here. It suggests that the fundamental reality is not one of objects in space, but of information and connection. It reframes Einstein's puzzle in the most astonishing way imaginable. The spooky action at a distance is not a strange phenomenon happening times within times, space-time. The spooky action at a distance, this web of quantum entanglement, might be what generates space-time in the first place. We are left with a universe that is profoundly holistic, interconnected, at a level so fundamental that it precedes space and time themselves. So, we find our journey has come full circle. We have tamed the spooky, transforming it from a paradox into a technology. We have answered Einstein's challenge, proving that reality is indeed as strange as quantum mechanics predicts. But in doing so, we have unveiled a new and even more sublime form of spookiness. We have peered behind the curtain of the classical world only to find that the machinery backstage seems to be woven from threads of pure connection. The story of entanglement is far from over. It remains one of the most fertile, most awe-inspiring, and most challenging frontiers in all of science. It promises to guide us toward a final unified theory of physics, to perhaps explain the birth of the cosmos and the nature of time. It reminds us that our common-sense intuition, honed over millennia of survival on a particular planet at a particular scale, is a profoundly limited guide to the ultimate nature of things. The universe is under no obligation to be simple or to conform to our expectations. Its beauty lies in its magnificent, confounding complexity. The spooky action at a distance is no longer a spectre to be feared. It is a signpost pointing the way toward a deeper understanding, a more connected reality, and a future filled with revelations that will once again forever reshape our place in the cosmos. The quest continues, driven by that most human of impulses to look into the heart of a great mystery and not to flinch.